I just wanted to introduce myself. I am Dr. Kate Lancaster, and I'm a senior lecturer here in the School of Physics, Engineering and Technology at the University of York. And I'm going to be your trusty chair for this evening. So I'm going to be chairing the Q&A at the end of the session. Just a few technical notes for the session this evening. Basically, if you're watching live, you can ask questions. So there's a Q&A button on the bottom, which will allow you to type questions in, and then I will be able to see those at the end and go through and see what the most popular ones are to ask, or the most interesting ones. So you can ask questions at any time throughout the talk when they come to you. So, and I'll be able to scroll through and see what questions you've asked. Should you have technical issues such as loss of Wi-Fi, you can rejoin the event using the original link. Also, remember today that today's event is being recorded, so you will be able to watch again if you enjoyed it that much and you'd like to see it again. Subtitles are available for this event. To turn these on or off, use the CC Live transcript button at the bottom of your screen. So that's the kind of a housekeeping part of the session. So I just wanted to introduce a little bit about these winter webinar series. Basically, what we're trying to do here is bring you examples of our amazing cutting edge research that we do here in the School of Physics, Engineering and Technology. We want to kind of give you a bit of a glimpse of some of the amazing stuff that we're doing, some of our wonderful physicists and engineers are working on. So to that end, other than tonight's lecture, which I'm sure you're very, very excited to see, we have another 3 exciting lectures for you to delve into, should you so wish. So after this lecture, there's another 3 lectures that you can sign up to. So Dr. Mohammed Nazar Esfahani is doing a talk discussing engineering at the nanoscale to create devices and systems that are not only small, but also capable of unprecedented performance in fields like medicine, electronics, energy, and environmental protection. Then Dr. Edgar Buchanan Baruman will be giving us an insight into the autonomous robot evolution project and talking about whether a robot could design and produce other robots. Not scary at all. And then finally, Dr. Stuart Higgins, who's a biomedical engineer here at the School of Physics, Engineering and Technology, will be talking about whether we can heal people with electricity. So we really hope that if you've enjoyed this talk, you want to sign up and join those talks too. We'd be delighted to have you along. So without further ado, let me kind of come on to the topic of the evening. So this is a topic that's close to my heart too. I also work in the area of fusion, which is what tonight's talk is going to be about. So obviously you're going to be interested in hearing about how we're trying to bring the power of the stars down and actually have exquisite control over it here on Earth. And Roddy's going to be taking you through the story of how we might do that. I've known Roddy for quite a long time, more than a decade, I think, probably getting on for 2 decades. He's a professor here at the University of York. And his main research is in the area of fusion, and he's particularly interested in trying to get electricity from fusion. I don't want to ruin the rest of his talk for you. Nobody wants to hear me blethering on. So on that moment, I will hand over to Professor Roddy Vann to give you his talk tonight. So thank you very much, everyone.
Hey, thank you for that very kind introduction, and thank you everyone so much for coming along. I was asked to speak on the topic of bringing the stars down to Earth, fusion technology for the future, which I think is a really good title to draw everyone in. My name is Roddy Vann, and as Kate says, I'm an academic in the School of Physics, Engineering and Technology, which is, and specifically the Plasma Institute at the University of York. Well, what gets me out of bed in the morning? What motivates me to work in my particular area? Well, I thought I'd start with a quote by Professor Sir Chris Llewellyn-Smith, compared to whom I have the IQ of a carrot. He was Director General at CERN, a science experiment you might have heard of. He was also in charge of the UK fusion programme, and he's now an emeritus professor of energy science at Oxford. Anyway, he gave a talk at the York Plasma Institute. This is taken with permission from a talk he gave about 10 years ago to us. And I'm going to quote, he said, "The biggest challenge of the 21st century is to provide sufficient food, water and energy to allow everyone on the planet to live decent lives in the face of rising, increasingly urbanized population, the threat of climate change and eventually declining fossil fuels." Science is really important. Science can be really exciting for its own sake. The reason I'm a scientist is because I want to make people's lives better. And I know that sounds really cheesy, but it happens to be true. So I've got an alternative, slightly less catchy title for today's talk, which is, "Might fusion be able to supply sufficient energy for everyone on the planet to live decent lives?" And to do so without destroying the planet through climate change. But I remain obviously the same person. So slightly less catchy title, but this is what I'm trying to do. And I'll perhaps try and adjust the first title as well. So my talk is only in 3 or 4 sections, and I've been told I do need to finish at 10 past, so I'll do my best to do that. So I'm going to start off by asking, what is fusion? Certainly, when I most recently just put fusion into Google, I found out all sorts of things about a particular genre of jazz music, which is great, but I'm not talking about jazz music, perhaps sadly. I'm going to be talking, at least initially, about some nuclear physics. So I'm aware that we've got and I hope that we've got a wide breadth of folk on this evening's talk. I'm aware that some of you have really quite a technical background, some with a slightly less technical background. The first few slides are a little bit more technical, and then we have slightly less technical stuff. So it doesn't matter if not every single slide makes sense. On the other hand, I hope that there will be, those of you who are more technically inclined, I hope there'll be the odd little bit to keep you thinking. Here is quite a famous, is famous the right word, a really important picture in science, which shows the amount of binding energy, the amount of energy that it takes to keep a nucleus together as a function of the size of the nucleus. So here we have size of nucleus along the horizontal axis. On the vertical axis, we have the average binding energy per nucleon. This basically means, so some of you will be aware that a nucleus is made up of neutrons and protons. This tells you how tightly they're bound together. And if you move upwards in this diagram, so either in this direction or this direction, you can get out some of that energy which is associated with holding your nucleus together. Quite a few of it up here. So here's a uranium atom. It turns out you can get energy by splitting a uranium atom, and it turns out you can also get energy out by sticking together small atoms. So here we've got various flavors of hydrogen, helium, lithium, some more helium. So here's common organic helium, if you like, carbon, oxygen. And there's a minimum around iron. So you can't get energy out either by splitting iron or sticking it together. So we do fission going from right to left and fusion going from left to right. And so what is fusion? Fusion is about getting energy from combining small nuclei. The idea here is to make energy. So we're seeking reactions. What I mean is combining these small nuclei down on the left-hand side that give us a high output energy that bump us a nice long way up on the vertical axis, and also decent reactivity at conditions that we can achieve in the lab. And that's what, if you like, the rest of the talk is really about. So here's a slide of some candidate nuclear reactions. So some nuclear reactions that we might try if we want to do fusion. That is to say, if we want to get some energy out. I'm going to define easiest on the next slide, but it turns out that the easiest reaction is between two heavy isotopes of hydrogen. What does that mean? So hydrogen, as a lot of you will know, is typically made, the nucleus of a hydrogen atom is typically usually made up just of a proton, nothing else. But it turns out that there are heavy isotopes of hydrogen where the nucleus has an additional neutron or two additional neutrons. So here I have a nuclear reaction. I'm going to try and talk you through this. Both of these are hydrogen atoms. The number down the bottom is the number of protons in each of these nuclei. So each of these things is a nucleus. The number down the bottom here, this suffix, is the number of protons in each nucleus, and the number up the top is the total number of neutrons and protons. So here we have a special hydrogen nucleus with 1 proton and 1 neutron, giving us a total of 2 nucleonic particles. Here we have 1 proton and 2 neutrons, gives us a total of 3. We stick these two things together and we get a helium nucleus. So helium always has 2 protons. And also this helium nucleus, as it happens, additionally has 2 protons, like most do, and a neutron. And importantly, we get a load of energy out. So this is a bit like a chemical reaction that a lot of you will have seen, but this is a nuclear reaction. And just like a chemical reaction, I have to balance the number of protons, the number of neutrons out on each side, and I also have to think about the amount of energy. So what's good about this reaction is that I get loads of energy out. Just a little bit of terminology is that this helium nucleus we call an alpha particle because it's super energetic. Helium nucleus, fast moving helium nucleus, is the same thing as an alpha particle. So suppose I want to do this reaction. Well, I need each of the fuel ions, right? We call this the fuel because we stick these together. This is a bit like a burn. If this were chemistry, this would be a burn and we get energy out. Deuterium, this D, this heavy hydrogen with one extra neutron, it turns out this occurs naturally, not tremendous. It's not tremendously abundant, but it's reasonably abundant because there's a huge amount of hydrogen around. So about 0.01% or about 1% of 1% of naturally occurring hydrogen is deuterium. So we can get this out of the oceans or other places where we've got lots of hydrogen. Tritium, unfortunately, decays with a half-life of just over 12 years. So there isn't much of this sitting around because if it's sitting around, then it's decaying. So we need to make it artificially, and I'll say how we do this a bit later on. There are a bunch of other nuclear reactions. A question that I sometimes get is, well, are there other reactions that we could look at? In particular, are there other reactions that don't produce a neutron? Why is a neutron bad news? Potentially, well, because if I wallop a neutron into a bit of metal, for example, that bit of metal typically becomes a little bit radioactive and it typically becomes a little bit crumbly. So this is sometimes not a good idea. So there are some fusion reactions which are aneutronic. They don't produce a neutron like this reaction. Sticking a proton and boron together gives us 3 helium particles, 3 alpha particles and some energy. But there are some problems with this reaction as well. So this is what fusion's about. We're trying to do reactions that look a bit like this. Why am I doing deuterium and tritium? Well, I'll tell you what, actually, I'm going to just zip. So we'll look at this technical stuff in a second, but I just want to zoom down to the bit on the right. So on the bit here and the bit on the right-hand side here. Here I have a figure where I have temperature in billions of Kelvin. So very high temperatures or pretty high temperatures here. So this is 1 billion Kelvin, 10 billion Kelvin here. And I have reactivity of various reactions. And I've picked 3 reactions from that previous slide. I've got deuterium, tritium, deuterium, 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 helium-3 from the previous slide. This shows the reactivity. And this is a logarithmic scale. So we're going up in powers of 10 here. And at the achievable sorts of temperatures or even sort of, well, yeah, these are still very high temperatures, but achievable sort of temperatures like 100 million Kelvin, it turns out that the reactivity of the deuterium tritium reaction is about something like 100 times greater than the next best. So this is why we choose deuterium and tritium. What am I going to say here? I'm going to zip through this bit here. I've defined reactivity if any are interested. People want to freeze the slide later and look through this. What it turns out is that the fusion power, more particularly the fusion power per volume, depends on the square of the density, because we want as much deuterium as possible and as much tritium as possible. It depends on the amount of energy out per fusion reaction, and it depends on the productivity. And you might imagine it's kind of intuitive, perhaps. It depends on the product of all those things. So the density squared, the fusion output per reaction, and the reactivity. And we'll come back to this a little bit later on. If you're interested in the factor of 4, then then that's great as well. But we're not going to worry about that too much. The next thing I want to do is we're going to take a number of concepts here and stick them together. So the next thing I want to introduce is a thing called the confinement time, which is a really important concept, in fact, across science, but in particular in fusion. So suppose we've got a bucket here. I stole this from a colleague of mine who generated this pretty brilliant sort of PowerPoint graphic. Here we've got some water sitting in a bucket. The bucket is perfect. And so this perfect bucket has an infinite water confinement time. However, buckets in general aren't perfect. They have holes in. They leak some way or another. Certainly most of the buckets in my garage do. And buckets with holes have a reduced confinement time. And we're going to define the confinement time as the time that it takes for half of the water to leak out. And what's clear from this is that the more holes and the bigger they are, the shorter the confinement time. I can keep the amount of water in the bucket the same by pouring water in the top, can't I? So if my goal is to keep the bucket full, I can do this by pouring in loads of water. But obviously, the worse the confinement, that is to say, the lower the confinement time, the more holes there are, the more water I have to pour in, which if I'm trying to keep my bucket full and have a finite supply of water, this is bad. But also, I've got to do something with all this water that's leaking out. And you might see where this analogy is going a bit later on. So confinement time fundamentally measures how effective the confinement system is. So how leaky is our bucket? Okay. Right, I've got one technical-ish slide here, and I hope it's okay if I go through this, because this gets us to somewhere, a criterion, a condition that you see sort of pasted all over sort of the fusion literature. And I'd like to get to this technical bit, if I may. Ignition is a word that we use when the power from the charged product, so in deuterium-tritium fusion, this means the alpha particle, exceeds the required heating power. Now, we can describe the lost power as the amount of stored energy divided by the energy confinement time, right? This is power is energy over time. The energy is the stored energy in the plasma in this case, and the energy is the energy confinement time. Now, we can then use the, and I hope it's okay, I'm sort of skipping through some of these bits, but the stored energy, we can use the ideal gas law. Some of might have done this at A level, will be doing this at A level. This is a formulation of the ideal gas law. We've jumped to factor of 2 because we've got 2 species in the plasma. So this is a statement of the ideal gas law. This allows us to relate stored energy to temperature and to density. So what's the ignition condition? The ignition condition is that the fusion power is greater than the amount of power that's being lost. From the previous slide, I know that the fusion power looks like the density squared times the fusion energy out per reaction times the reactivity. This has to be greater than the rate at which we're losing power, which in steady state is the amount of stored energy from the ideal gas law over the energy confinement time. I can do some jiggery pokery taking this up here, this over here, and I get a condition which tells me that the density times the temperature times the energy confinement time has to be bigger than some quantity, which has involved in it the energy out from a given fusion reaction, the temperature and the reactivity. But as we'll see on the next slide, this thing, the reactivity over the temperature, has a maximum for a given reaction. So this means that for deuterium-tritium fusion, this so-called triple product because it's the product of 3 things, the density times the temperature times the energy confinement time, has to be bigger than a given number. And this is a thing called the Lawson criterion. Why have I bothered going through this technical stuff right at the beginning of the talk? Because this gives us a success criterion for fusion. If we want to do fusion, our fuel has to be sufficiently dense, that's the letter N, has to be sufficiently hot, that's the letter T, and we have to have sufficiently good confinement time, that's tau E, that we can exceed this number, and then we're good to go. And we're going to spend the rest of the talk thinking about how do we achieve this condition. Okay. Now, perhaps a couple of slightly technical bits here. Perhaps the only bit which is worth saying is that this is a necessary but not a sufficient condition for success. And if we're away from the optimum temperature, which for deuterium-tritium, it's shown on this graph here, is about 100 million Kelvin. Is that high? It's probably quite hot. I mean, if there was that temperature in your living room, you probably wouldn't like it very much. But so it's hot, but it's as I might be able to justify a bit later on, it's broadly speaking achievable. If we're away from this optimum temperature, then in fact it turns out it gets worse and worse. It gets harder and harder to achieve this condition. So this is a necessary but not sufficient condition. This form of criterion is useful because quite a lot of fusion technologies are constrained by maximum pressure. Pressure is density times temperature. Some of you will have noticed I've thrown out Boltzmann's constant. Happy to discuss how I've dealt with that. It turns out that if you have an energy confinement time of about a second, then it turns out the pressure ends up being a few atmospheres. And I'm not going to click on it because I don't want to take up too much time. I strongly recommend using Google as a calculator, and you can put units into Google as a calculator, and you can do this calculation. It turns out that if you had an energy confinement time of a second, then to satisfy this condition, you'd have a pressure of a few atmospheres, 4 or 5 atmospheres. And this is interesting because it tells you that the pressure in a fusion plasma might not be that far off atmospheric pressure, in fact, even though the temperature would be really high. So I want to summarize this first section and think about where is the power going in order for us to be able to do fusion. So we have some fuel, that's indicated by this red block here. I'm going to talk much more about the fuel. That's going to be part of the, if you like, the physics content of this talk in a minute. I've got to put in some input heating power. Why is that? Well, because I've got to get the fuel hot enough that those nuclear reactions happen, then I start getting energy out. If I'm lucky enough to have a wood burner at home, if you've tried lighting a fire, a wood fire, you know that you've got to get it hot, burning hot enough that the fuel starts to burn and that the burn is self-sustaining. So we need some input heating power. Fine, okay. We also are going to have some exhaust. power. If you drive a car, you know that you have some heat loss through the exhaust, and we've already looked at what this is going to be. This is going to be the total stored energy over the energy confinement time. Fine. But if we're being successful, we're going to generate some power through fusion. Let's call this P subscript fuzz. This is the output fusion power, but this is going to have two bits. There's going to be a bit going to the neutrons, and there's going to be a bit going to the alpha particles. So I'll show this other arrow, but I'm going to talk about the neutrons first. The neutrons are not charged. They're lost extremely quickly. The energy in the neutrons, and in fact 4/5 of the energy is lost to the neutrons. Why? Well, because those of you who care about conservation of momentum will know that the alpha particle is 4 times heavier, is 4 times the mass of the neutron. So by conservation of momentum, 4/5 of the energy goes to the neutrons and 1/5 goes to the alpha particle. Okay, so the energy from the neutrons, this is the energy that we capture, and this is the energy that we turn into electricity. This charged particle, the energy in the alpha particle, we want to stick back into the fuel so that we can reduce the amount of input heating power. So a good confinement, that is to say a large energy confinement time, means that we have to put in less external heating power here, and we also have less exhaust to manage, and these two things are good. So a lot of what we're trying to do in fusion from a scientific point of view is try and get a big confinement time, tau e. So let me get to this stage. I've broken slightly my PowerPoint overlays here. Anyway, never mind. Right, so here we've got a diagram. This shows what we're trying to do, but we've now added another level of complexity. So we've got down the bottom here, we've got this reaction. Pardon me. Here we go. We've got deuterium fuel coming here. I combine tritium with deuterium. This gives me a neutron plus a alpha particle plus power. So this here is my primary fusion reaction. Tritium plus deuterium goes to neutron plus an alpha particle plus power. But you might remember me saying that tritium up here is not naturally occurring. We've got to generate it. And the way that we do that is we bombard our fusion-produced neutron into a lithium atom, and a lithium atom, when bombarded with a neutron, produces tritium and an alpha particle and some more power. So in fact, we've not just got one nuclear reaction that we need to do. We're going to do 2 nuclear reactions that look like this. However, and so we've got to confine all of this lot. Doing this requires some level of containment. But these 2 reactions are happening in different places. The deuterium-tritium reaction is happening in a plasma, and I'm going to talk about that in a minute. And the neutron-lithium reaction is happening in the vessel wall, sometimes called the blanket that's surrounding our fuel. And I'll draw some cartoons of this in a minute. Why have I drawn a picture of a sailing boat? Well, I like sailing, so I thought it might make us all happy to see a sailing boat here, although the sailing boat doesn't seem to have much wind, which is perhaps sad. But the reason I've done this is because we get deuterium from hydrogen, and there's lots of hydrogen in the sea. Why have I drawn a picture of a laptop up here? Well, one of the places you can get lithium from is laptop batteries. Or put another way, the amount of lithium in a laptop battery is enough to give you more or less your lifetime's electricity supply from fusion. So and we're pretty good at giving people laptops and mobile phones, aren't we? So this is, yeah, I mean, I guess you could recycle your laptop, or you could just dig it out of the ground in the same way that you do for a laptop battery. Anyway, so we've got these 2 reactions, and we've got this. It's almost a cycle, right? And then we have our product. So we get power out here and we get power out here. And the power out here, particularly because this is the reaction which produces most energy, we want to stick on the grid. This is how we're going to make electricity. Right, quite a lot on this slide. I've got this slide largely for completeness. Here's the reaction where we're getting most of the power. I've said deuterium is naturally occurring. Tritium, challenging. ITER, which is big prototype power plant being built in the south of France, will require about 3 kilograms of tritium just for startup alone. This is quite a big of the global tritium market. It's also quite expensive. Tritium currently costs about $30,000 a gram. Cost might go up. probably affordable for a really big project, but it's certainly not cheap. And I've realized I hadn't written down the reactions where we're taking the neutron from this reaction, we bombard it into lithium and we make tritium. One of the reactions is exothermic, one is endothermic. Annoyingly, the exothermic reaction is with lithium-6, which is less abundant than lithium-7. So what do we do? Well, we try and make, from every neutron we produce here, we try and make more neutrons. And one of the ways we do that is by sticking the neutron into a tritium, into a neutron breeder, which might be something like beryllium, but I wouldn't want to have any beryllium in my house. It's pretty unpleasant stuff. Anyway, big challenge for fusion. UK have launched a thing called the Lithium Breeding Tritium Program. Nice acronym, Liberty. Go and have a look at their website if you're interested in more of this detail. So how are we going to achieve this big triple product? Well, there are essentially two approaches, and they are contrasted, yes, by the technique, but also how they're trying to get the density times the temperature times the confinement time really big. In magnetic confinement, what we're trying to do is achieve moderate pressures, so moderate density times temperature, perhaps just a few atmospheres, but a really long energy confinement time, so perhaps even a second or so. And the most successful approach to magnetic confinement fusion is the tokamak, which I'll discuss shortly. And then the contrasting approach is inertial confinement fusion, in which the confinement, such as it is only because the fuel has finite mass. Kate, who kind of introduced me as an expert in this area, here the confinement time is very small, but the pressure is huge, and this is achieved perhaps using lasers. And we've got a picture on the inside of a tokamak, so a magnetic confinement fusion device, top right, and some of the lasers from the National Ignition Facility in the US, an inertial confinement fusion device on the right-hand side. But whichever approach we take, the fuel is going to be at millions of degrees. So we need to investigate something called the plasma state, and so that's where we're going next. We're going to our next destination is some plasma physics. So there we go. Next title: some plasma physics. So what's plasma? What's this word that I'm using? Plasma. So plasma is the fourth state of matter. What do I mean by that? So down the bottom here, we've got some states of matter we're quite familiar with. So if I take water and I make it really cold, I get ice, which is a solid. What's going on in a solid? Well, I have some sort of lattice where where I've got atoms or molecules which are neighbors of other atoms or molecules, and although they wobble around a little bit because they've got finite temperature, a given molecule or atom retains its nearest neighbors. Its nearest neighbors don't change. I heat it up a solid a bit, and what happens? Well, then the molecules or atoms are able to move around a bit and they change neighbors. Now, what happens in a liquid is that change of neighbor happens relatively slowly in some sense, but it's definitely the case that if you look a bit later, a given molecule has got different neighbors to what it had previously. Liquids are kind of complicated, actually, right? There's quite a lot of physics that's going on in liquid. Perhaps it's a bit easier to understand what happens in a gas. We've then broken any residual bonds, any sort of solid-like bonds that were kind of higher order bonds that we had in a liquid, and now we haven't got any bonds at all between constituent molecules. So in a gas, whether that's water vapor or it's oxygen or nitrogen, I've got the molecules wandering around and they basically don't interact with each other unless they're in the process of bashing into each other. So I've got a bunch of neutral molecules, right? A nitrogen atom or an oxygen atom or a water molecule. These are each neutrally charged and they only really interact with each other when they bump into each other. But the bonds between them are broken. So what happens as I add further energy, because that's what I'm doing here, right? I'm adding energy. This is the same as increasing temperature as I go from left to right here. So what happens if I take the air in the room, let's say, and heat it up lots, then I get plasma. And what I'm doing is I'm breaking further bonds. That's the pattern here, right? If this were only connect, right, what would I be doing? I'd be breaking more and more bonds. And in the gas, what bonds are there left to break? Well, in particular, there are the bonds that have got the electrons stuck to their host nuclei. So if I rip those electrons off the nuclei, I end up in this fourth state of matter called the plasma. So the plasma is an ionized, I almost said electrically charged. Overall, it's more or less neutral, but its constituents are negatively and positively charged. And usually in a plasma, we have, well, electrons are always negatively charged. And in all the plasmas I'm going to be concerned with, the ions are positively charged. So the electrons are going to be negative. They're going to be very mobile, move around really quickly. And the ions are going to be positively charged, relatively heavy, much less mobile. But it doesn't behave like a neutral gas. Why not? Because in a neutral gas, the neutral the molecules in a neutral gas don't interact with each other really unless they're in the process of bumping into each other, going through some sort of binary collision, like a couple of billiard balls and like a couple of snooker balls. But in a plasma, because all the particles are charged, they can feel each other's force everywhere they're in the plasma, or at least over a much longer range. So in a plasma, we get coherent behavior that we don't get in a neutral gas. All right, time, fine. Okay, so Kate will come back later on and she can tell me if I've kind of got this right. But how does inertial confinement work? Here's a little bit of inertial confinement fusion physics. So here we have a pellet of deuterium-tritium fuel, which is typically solid. To give you an idea of the scale of experiments, this is perhaps a few millimeters across. So it's frozen deuterium-tritium fuel in a plastic shell. The blue thing here is a plastic shell. And then I've indicated here by driver, this is a heating mechanism, which is often a laser, a very powerful laser. This heats up the shell and the fuel extremely quickly. The shell ablates. What do I mean by ablate? The shell is extremely hot, so it flies outwards. By conservation of momentum, Newton's third law, if you like, this then compresses the deuterium-tritium fuel. By rocket action. This is Newton's third law, right? And as it compresses, it heats and thereby achieves the conditions for fusion. We get a central hotspot, and then this releases alpha particles. And those the neutron, it also produces neutrons. Those are lost pretty rapidly, but the alpha particles then move outwards and continue to heat the fuel and sustain the burn. But there's nothing keeping this fuel there. It's a big hot ball of gas, and ultimately it flies out. But the temperatures and the densities are extremely high in an inertial fusion reaction. Okay. So Kate knows more about that than I do. My expertise is in magnetic confinement fusion. So how does magnetic confinement fusion work? Right, in the picture in the top here, I've got some plasma particles in the absence of a magnetic field. Now, they interact with each other. So perhaps some of these are ions and some of them are electrons. That this thing can feel the force of this thing, but they move around still more or less randomly. I mean, yes, you could set up waves in this plasma, but there's nothing confining this plasma. It can go off and hit the wall. However, let's suppose that we get a big magnet and impose a magnetic field. These straight black lines here are meant to represent a magnetic field. It turns out that, and some of you who are doing perhaps A-level physics or something at the moment will know that if you have a magnetic field, then particles gyrate around those field lines. They go around in circles around those field lines, and the rate, the frequency with which they go around those field lines depends on their charge and on the magnetic field strength and the mass. And this is pretty well understood. Now, it turns out that particles, because of this gyration motion, if you give one of these particles, suppose I give one of these particles a kick and I try and kick it across the magnetic field, then all that happens is it goes round in a slightly bigger orbit or a slightly smaller orbit, depending where in its motion I've given it a kick. So but if I give it a kick along the field line, then it flies more or less freely along the magnetic field line. So this is a little bit like a bead on a string in some sense. The particles are more or less confined, not quite, but they're more or less confined to the magnetic field lines. So if I want to confine my hot deuterium-tritium fuel, perhaps I've got a starting point here because the fuel ions are constrained to the magnetic field lines. Problem. This is like a bracelet where I haven't done the ends up. And any of you who've made a bracelet and stuck some beads on it and forgotten to tie a knot in the end will know how frustrating it is when all the beads fly off the end, right? So what are we going to do? We're going to do what we do when we make a bracelet, which is take this end of the field line, this end of the field line, and join them together. So I'm afraid the color scheme doesn't match, but what I've done here is I've taken this blue thing here, this blue tube, and I've joined the ends up. I've joined this field line end up with this end and so forth round. Unfortunately, this is coloured in pink, but here is my pink plasma. So we've bent the magnetic field lines round into a ring. This is sometimes called a torus. This donut shape or bicycle tire shape is called a torus, and we've done this to prevent the end losses. So we've generated what we've called a toroidal field in this geometry. In a toroidal geometry, we have two directions. Toroidal goes around in this direction, poloidal goes around in this direction, and the field that we had, the field here, this one that goes around in the direction of the plasma, we call the toroidal field that goes around in this direction. So you might think, but oh, and why have I got these gold rings? And I've obviously made a mistake because I've got 4 gold rings, and you should always have 5 gold rings. But anyway, what are these 4 gold rings here? These are here because if I pass an electric current through them, I get a field round in the toroidal direction. So even though these currents are in the other direction, which we call the poloidal direction, these generate if I pass electrical current through these coils, I get a field in the toroidal direction, round in this direction. However, it turns out if we were able to do a couple of lectures of plasma physics, we'd find that a toroidal field isn't good enough. It turns out that if you put curvature in the magnetic field, then the particles drift relatively slowly across the magnetic field lines, but they do drift across the magnetic field lines sufficiently quickly that just a toroidal field doesn't work. And so we need to put on a poloidal field as well. So we've got a toroidal field going this way, we've got a poloidal field going around in this direction, and this then gives us a helical field. So we've got a helical field which goes around the plasma in this direction. So how might we generate this helical field? Well, we've done the toroidal field. We do that by sticking a current carrier through the middle of the plasma here. And how do we generate the poloidal field? Well, one way of doing that is by putting a current through the plasma. What's one way of doing that? Well, one way of generating a current in the plasma, well, we've got electrically charged or ionized gas here that conducts electricity. So what I can do is use a transformer action. So what's transformer? I put a changing current in a primary coil. I link the flux. Some of you will be very familiar with this through A-level. I link the magnetic flux to this single turn secondary. That then generates a current through because of the induced EMF in the secondary. That current then generates a poloidal field, which I add to the pre-existing toroidal field. Okay, great. So this is a really helpful cartoon for how a tokamak works. So just to make that point again, the relatively slow drift of charged particles across magnetic field lines necessitates a poloidal magnetic field. And we sometimes hear about tokamaks. I think I've already used the word. A tokamak is a toroidal magnetic confinement fusion device. It comes from some Russian words, in which the poloidal field is generated specifically by the plasma current. So by generating a current in the plasma. Now, transformer action, as we all know, relies on a changing current in the primary coil. Well, this is all very well, except that there comes a point at which I'm driving so much current in this primary coil that I know it melts. That would be bad. Or I run out of power supply. That would be bad. So transformer action is only good for pulsed operation. It's no good for steady state operation. And I quite like my power plant, please, my fusion power plant, please, to operate all the time, not just some of the time. So we can't do this we can't use transformer action in a power plant. So what can we do instead? And I've got this bullet in here largely in the next slide, largely because this is my particular research expertise. Stuff I'm interested in is using microwaves. An alternative technique, instead of using transformer action, is to generate a current in the plasma using high power microwaves. And for example, the UK STEP project, which I'll talk about a bit later on, anticipates putting in around about 200 million watts of microwave power. So what's a kettle? A kettle's about a kilowatt or so. So something like 100,000 kettles of power at about 100 billion cycles per second. And here's a picture of a tube which generates that sort of microwave power. This is about, just to give you an idea, come on, go back slide. This is about the same height as a person, to give you an idea. Okay, so microwaves and tokamaks. Microwaves and tokamaks are really cool, and whatever you think your career you're considering now, you should change it and work in microwaves and tokamaks because it's the best. What's a microwave? Well, microwaves are just words that we give to electromagnetic radiation in this sort of frequency range, so from about 10 billion cycles per second to about 600 billion cycles per second. This corresponds quite nicely to vacuum wavelengths that are macroscopic, that we can think about, right? That are about 1 millimeter to about 1 inch, this sort of size, right? These are sufficiently high frequency, actually, that ions remain effectively stationary. It turns out ions are sufficiently massive, they don't really feel wiggles this fast. There are important applications for microwaves and tokamaks. Diagnostics, I spend a lot of my time doing effectively electronic engineering, building really advanced radar systems to see what's going on in tokamak plasmas. But also, as I mentioned on the previous slide, we use very high power microwaves for driving current in tokamaks. And it turns out that the microwave technology is very well suited, translation, to use in power plants for reasons I can discuss later if you want. If you're interested in physics, why should you study microwaves and tokamaks? Well, one reason, I'm just going to try and go forwards and backwards. Excuse me. So here I've got a video of a simulation of a microwave beam going through. These are density perturbations in a tokamak. The optics of microwaves going through plasmas is really cool. It turns out that the propagation depends on the polarization. So you've changed the direction of the electric field. This changes the relationship between the frequency and the wavelength. It also depends on the direction with respect to the background magnetic field. Some waves even have a negative refractive index. That is to say that the wave fronts are going this way, but the energy of the wave is going the other direction. This is pretty cool. And sometimes you think this has to be a pretty exotic kind of material. But in fact, in plasmas, we've known about for a while, we've seen this. It happens in the ionosphere, which is in the next bullet. So if you can do microwaves and tokamaks, you can understand some communication problems in the atmosphere. And a research problem. There are a number of research problems that we're attacking here at York and with collaborators elsewhere. This video here shows a microwave beam coming from the right-hand side, going through some wobbles in the plasma. And it turns out that because this microwave beam is interacting with these fluctuations in the plasma, we've injected a microwave beam here. We were hoping that it would end up kind of where the laser pointer thing is now. And it turns out a big chunk of it ends up over here. This is really bad if you've designed a multi-million-pound fusion project, which is reliant on your microwaves ending up in the right place. So this we want to properly understand. This is from some of my collaborators at Stuttgart, actually, were led by some colleagues at the University of Stuttgart. These wiggles that I showed you on that last slide are super. Time. Right, I'm going to finish in 3 minutes in case Kate's listening. I'll finish in 3 minutes. Sorry. So okay. So turbulence is really important. Another really big research interest at York. What's turbulence? It's when you wiggle stuff lots. If you take a boiling kettle, for example, the transport in that boiling kettle is not. It's like. Is it like really strong convection? A little bit like really strong convection. Anyway. Plasma turbulence, so how, and the point is that turbulence is what determines how heat is transported from the inside of your tokamak to the outside of the tokamak. Despite decades of effort by some very clever people and some really big programs running on huge supercomputers, we still don't understand how plasma turbulence works. So please join the community and help us fix it out, help us figure it out. And part of the reason is the huge range of length scales we have to simulate across and understand across. A typical code, computer code takes thousands of cores, uses up thousands of cores for weeks at a time. And this is for a relatively straightforward linear simulation. You want to do a non-linear simulation, a single simulation could take months on some of the biggest supercomputers in the world. So what's the current status of fusion? I'm just going to make 2 or 3 statements about this, and I might jump through over the odd slide. So we're making lots of progress, and we've made progress over the last few decades. Over in the past, tokamaks have focused effectively doing plasma physics. Only 2 tokamaks ever have run with tritium, and they typically run with just deuterium because that doesn't make neutrons, which makes it cheaper to run. Future research, current research actually, is even different from the past. We're trying to figure out how to build power plants. We're less interested in the science for the sake of it, and we're increasingly interested in how do we make fusion a commercial reality, and that's illustrated by some of those bullets. The UK has a leading position in the global fusion community. JET, the Joint European Torus, was the most advanced tokamak in the world till it stopped operating last year. 23, back end of 23, got some really exciting results. These things are big, right? There's a standard person here. There's another standard person here. These things are really big. The decommissioning of JET will provide the UK community with unique expertise. Really exciting project, even as it goes on. ITER is the International Prototype Power Plant. Brilliant. It's being built in the south of France, which is nice, very nice place. The first plasma, late 2030s. It's planning on producing about 500 megawatts of fusion output power. The engineering is outrageous. This is like something off Moonraker, right? Here are some engineers, these are real people. This is an artist's impression. This is I think it's 1/12, or is it 1/8? 1/12, I think, of the vacuum vessel. The engineering is just absolutely outrageous. And one of the challenges is, particularly with ITER, is we've got to stick all the different bits together. And I'm not going to go through them in detail, but integration of the components is a real challenge. Can we go faster? Yes, we probably can, right? I think that fusion is most likely to succeed if we pursue lots of diverse diverse approaches, and also if we can involve the private sector. And there are now something like 40 or 50 startups around the world, some of them now quite mature companies, which are supporting fusion alongside public government projects. And I'm going to jump over the UK's domestic tokamak. I can talk about that more if people want. Really exciting. The UK has decided that it's domestically within the UK. We're going to build a prototype power plant. It's going to be called STEP. It is called STEP. We've just come to the end of a 5-year feasibility study. The University of Warwick was heavily involved in that. We've set up the legal framework for doing fusion in the UK. It's going to be different from fission, which is really important. That's proportionate and it's very sensible. It's going to be built in North Nottinghamshire. So those of you who are close to York, it has a Doncaster postcode, in fact, as West Burton, so not that far from Yorkshire. And the site is now being developed, and this is an idea of the time scale. Anyway, I'm happy to talk more about STEP. Super exciting UK project. I won't talk about stellarators. I just want to summarize with a couple of points. The big summary is that the fusion future is super bright. Fusion has some unique benefits. It is fundamentally safe in the sense that if something goes wrong, the reaction simply stops. There is no runaway. There are no direct greenhouse gas emissions. The fusion reaction doesn't produce carbon dioxide in some sort of direct sense. It can deliver a steady baseload supply, so you can switch it on. It can run 24/7. There's plenty of fuel, and there's relatively little waste with and it's only mildly radioactive in a relative sense. So this is all really good. There are some big challenges. What do I want to? I'll tell you what, I'll leave this slide up in a second. I'll go back to this slide. This is my final slide. Thank you so much for coming this evening. I'm going to take some questions in just a second. Please engage with fusion. There is a fusion course or a fusion career out there for you. If you're at a school or a college, we deliver outreach and guest talks. There are FusionNet teaching materials available online. Do take a picture of this slide if you want to. If you think about being an undergraduate, do a physics course at a university like York, where Kate and I, who work in fusion, can make the electromagnetism homework problem about fusion. If you're an existing undergraduate, do a summer research internship and we can help you pay for that. Do the MSc in fusion energy, do a PhD in fusion. If you're in industry already, go to the Fusion Industry School and find out more. If you're an industry leader, then bid for work at UKEA or at STEP. There are lots of challenges. The biggest is probably we don't have enough suitably skilled people. But we're very keen to work with you to help if you want to work in fusion. And it's not just scientists. Yes, we need scientists, we need engineers, but we also need people who can run big infrastructure projects, can explore the legal space around fusion as well. Right, I've spoken too much, but thank you for being here and thank you for listening.
Okay, thank you so much, Roddy. That was a fantastic whistle-stop tour through the wibbly-wobbly world of fusion, and hopefully some of you might be excited enough to want to come and join us in the mission of delivering, well, clean energy to Earth. Essentially, it's not a small task. So now it's time for some questions. So I'm just looking through some of the lovely questions you've left. Here's a nice one. How do you measure, I'm paraphrasing here, but how do you measure the temperature of a plasma?
Right. This is an excellent question. Right. I think this is, so Kate, yeah, this is a good question from Kate. So, you know, to quiz me on this one, right? So, the plasma is so hot and so dense in a fusion power plant that you can't stick in a thermometer, right? This is probably where the question is coming from. So what can you do? I'm a microwave person. It turns out that the microwaves that a tokamak plasma emits go like a black body. So a tokamak plasma is optically thick to microwave radiation, which means that if you can measure the intensity of the microwave radiation at a particular frequency, you can figure out what the temperature is. Kate, what happens in inertial confinement fusion plasma? How do you do that?
Neutrons mainly. So you can measure the spectrum of the neutrons coming out and look at the width of the peak, and that relates to the temperature of the ions that exist in the plasma. But we can also use particular characteristic X-ray lines, which also tell us something about the temperature as well. So
Okay. I wonder, right. So another thing we do in, sorry if I may, because I want to talk about lasers. Another thing that we do in tokamaks, it'd be interesting to see if this works in power plants, but that we do on current tokamaks is we send in a laser this way, let's say into our fusion plasma, that then bounces off electrons, and then we look at the laser in a perpendicular line of sight, and the Doppler shift, so the width in the laser, in the resulting laser spectrum, tells us how hot it is, and the amount of laser light we get back tells us how dense it is actually as well. So there's that option as well. But yeah, I like microwaves.
okay, right. Thank you for that, Roddy. We've had a question here saying, can you use superconductors for fusion reactors?
So possibly a really disruptive technology, and I mean that in a positive sense, for magnetic confinement fusion, is the development of relatively high temperature superconductors, and in particular superconductors that you can make into, I was hoping I almost had a roll of sellotape, right? But it looks like a roll of sellotape. So extremely thin tape-like material that you can coil, that you can make lots of turns of in a very compact way. And this means that you can generate really high field magnets in ways that weren't possible previously at slightly higher temperatures. So possibly an absolutely massively disruptive technology, but really might be quite a game changer. Tokamak Energy are a UK company based down in Didcot, so just a little way south of Oxford, and they have a lot of intellectual property tied up in. It's a matter of public record. This is an area they are absolutely expert in, this UK company, in building high field magnets, superconducting magnets for tokamaks.
Excellent. So what about, this is more technological, what kind of materials are used for the walls of the reactor?
The answer is kind of dull in the sense that it's fancy steel. So we take and some of this, I should say, is done through, so not my area of expertise. Some of this is done through trial and error, right? But different steel, what do you watch? So fundamentally, what have you got to try and do, right? You've got to withstand huge, massive heat loads, tens of megawatts per square meter. So that's like the heat loading on the, that's comparable to the heat loading on the space shuttle on re-entry, but not for a few minutes, but for months or years at a time, right? But that's also an environment where you're not just getting lots of heat, but also you're getting lots of neutrons. The primary material is likely to be steel. In front of that, you may well put a layer of tungsten. You also need to breed tritium, so at some point you need some lithium in the wall, but probably tungsten in front with steel immediately behind it.
Yeah. And that's, we don't need the tungsten so much with inertial confinement fusion, but yeah, we because our chambers are bigger and so forth, which actually leads us on to a really interesting question here, which has more advantages, magnetic or inertial confinement fusion?
So at the risk of being really cheesy, I kind of don't mind which gets over the line, right?
Same.
I want us to make energy for people to use. I think if you both technologies have a number of challenges to overcome. I think if you look at that measure of the triple product, well, you need to measure it in different ways, right? I would think that, well, I think that we have a fairly good route to solving the problems that we need to solve for a tokamak in order to get electricity out and onto the grid.
Yeah. Yeah, I mean, I think obviously as well, well, not obviously, you maybe don't know this, but we've had pretty large breakthrough in terms of inertial fusion this year. So what we've managed to do is demonstrate that the technique is actually possible. Now what we need to do is move it to what we call very high gain, as in lots and lots of energy out for a given laser energy in. So that's kind of reassuring in that respect. And I guess another advantage to inertial fusion is that the main gubbins of your driver are very far away from the plasma and what's going on, because the plasma is tiny in inertial fusion, whereas I guess in a tokamak you've got the hottest place in the world closely followed by the coldest place in the world, so that could cause some issues, I guess. But as Roddy says, I don't care which one wins, I just want it to work, right? So yeah, but this is got lots of really good questions here, right? So we've got 5 minutes more, so that's great. We can do a few more. Let's see. What are the major alternatives to tokamak designs?
Yeah, so in magnetic confinement fusion, the biggest, there are a number of ideas, right? There is an idea that you use there's a concept called a mirror device, where you have, it turns out that to lowest order, you can confine. I showed that picture where I had the magnetic field just going straight across the page. It turns out that if you make the magnetic field really strong at the ends, it turns out to lowest order, this confines a large chunk of the plasma. This is called a mirror machine, because the particles bounce between those two so-called mirror points. There are a couple, well, there's at least one serious private company that thinks they've overcome if you like, the textbook problem to a mirror machine. That would be really nice, because it's a really simple geometry. But probably the leading alternative to a tokamak is a design called a stellarator, in which the confining colloidal field is not generated by the plasma current, but is generated by a bunch of really funky looking coils, very carefully engineered coils that are placed around the plasma. The leading stellarator is in Greifswald in the far east of Germany. It's called Wendelstein 7X, and you should go and visit it if you can. It's an amazing piece of engineering. It's been operating now, time flies, certainly 5 years. But yeah, and that's up and operational. Not a power plant, but it's a high performance plasma device.
So I think I've got one more question, because I think it might take a little bit of explaining. But we've had a couple of people asking about, obviously fusion is billed as a clean technology, but we know that there is waste associated with it. Could you just tell us a little bit more about that, and how that compares to, say, a fission power station?
Yeah, right. So the first thing is, I need to do a little bit of a disclaimer, in the sense that I'm a plasma physicist. I'm not a decommissioning expert. Well, I mean, that's worth saying, right?
Yeah.
So I'm not going to be able to talk about this in huge detail. The other thing, which is really exciting, is that we will be able to decommission jet as though it were a power plant, which will give us a load of unique expertise. The next thing is that at the moment we've got, and in fact there are many ways in which the UK is leading this. We're developing the legal frameworks to understand how fusion safety will work, right? Because we can't afford to make a mistake here, right? We have to, as is the case in any new technology, we have to make sure that we're safe at every step of the way. And of course, this means we have to build in safety at the design stage, as well as through the operational phase and the decommissioning phase. The sort of lifetime of fusion waste. Now, I need to predicate this by saying this is what I've heard and this is what I understand, but is of the order of decades. Let's call it 100 years. I'm pretty confident that we can keep. And so what you do, you put it in a concrete box for 100 years, and then you dig it out again afterwards. The level of radioactivity is, I understand, in the same category as the radioactive waste that comes from X-ray departments in hospitals. I think it's a bit more than that. I think that the activity is a bit higher than that, but it's in the same safety category. So it's not. So the peak activity is not super high, nor is it radioactive for a very long time. So I think if you wanted to be, I think ideally you take it all apart and then isolate the most radioactive parts. But if you like, a dumb brute force approach would just be to put a big concrete lump over all the top of it. Just so I've said this point as well, which goes slightly outside the scope of the question. I said it briefly in the talk. If you lose control of a fusion reaction, what happens is it stops. And this is really important. And the reason this is a really important concept, and the reason for this is that the density, the total, and consequently the total amount of fuel on site at any one time is extremely small. So the temperatures are really high, but compared to solid densities, the densities are very small. And Kate's fuel pellet is just like tiny, absolutely eeny weeny. So whether you're doing inertial confinement or magnetic confinement fusion, there is no runaway. Kate, have I got that about right, do you think?
I think so. Yeah, fantastic. So, okay, so we're going to have to draw it to a close here. So I just want to thank, and I'm sure on behalf of everyone on this webinar, to thank Roddy for his time and for his expertise in this area and for giving us a great talk on what's happening in the world of fusion at the moment. So all that remains for me to say is to thank Roddy once again and have a wonderful evening, and hopefully some of you will come and join us in the fusion mission in the future. Thank you so much.
Thank you everyone for coming. Goodbye for now.